Alright, in this video we're going to introduce the concept of Le Chatelier's principle and how to use it to predict changes in equilibrium that are useful for an AP Chemistry free response question. So the statement of the principle, which you should know, is that you have a system that is at equilibrium, a closed system at equilibrium, and a stress is applied to the system that disturbs the equilibrium. In response, the equilibrium shifts in a direction forwards or reverse that reduces the stress. If you look up Le Chatelier's principle on the internet, you'll find lots of different explanations that are worded very similar to this. Find one that you like and basically memorize that. You have to know a statement of the principle. There are different kinds of stresses that can be applied to an equilibrium. The stresses have to be things that affect either the reaction quotient or that affect the rates of the forward-reverse reactions. So changes in concentration can be a stress if they refer to gases or aqueous species in the equilibrium. Concentrations of solids and liquids cannot be changed. They're essentially constant. If you have a large piece of solid substance and you take half of it away, the concentration of that solid substance hasn't changed even though you've got less of it. Same thing for a liquid. If you consider, for example, water's concentration is 55 moles per liter. A large sample of water versus a small sample of water, the concentration is the same. So for liquids and solids, concentrations are constant, and therefore they don't act as stresses in equilibrium. Changing temperature will be a stress because it affects reaction rates and Kc. Changing the volume of the container, the vessel, will also be a stress because that will affect concentrations and pressures of gases inside. So that's a stress when there are gases involved. An example of an equilibrium system is the Haber process. This is the production of ammonia gas, NH3, from nitrogen and hydrogen gases. The reaction's balanced here, and beside it we've written that delta H for this reaction, the heat of reaction, or if you like more precisely, the enthalpy change, is negative, less than 0. When delta H for a reaction is negative, this reaction is said to be exothermic, and therefore we would write the word heat on the right-hand side of the equation along with ammonia. If delta H were positive, it would be endothermic, and we would write the word heat over here on the left beside the nitrogen and hydrogen. The first stress we'll consider here is a change in concentration, and more specifically, let's add some hydrogen to the system. To model that, we see this graph. In the graph, we notice that initially, all three gases are present, and their concentrations are not changing over time. Therefore, this initial situation would be an equilibrium system. That's the first requirement for Le Chatelier's principle. We have a system at equilibrium. Then, at this time here, where you see the dotted line, if you look at the hydrogen curve, you notice there's a sudden spike in hydrogen concentration. That sudden spike is caused by the addition of hydrogen at that time. So there's the stress that was applied. And now you'll notice that as a result of that stress, the hydrogen concentration drops, the ammonia concentration rises, and the nitrogen concentration drops, until at this new dotted line, all three gases again plateau, their concentrations stop changing, and you've reestablished an equilibrium system. In the new equilibrium system, notice that you have less nitrogen than you did originally, you have more ammonia than you did originally, and you have more hydrogen than you did originally, but you have less hydrogen than you did immediately after the stress. So the amount of hydrogen right after the stress decreased along with the nitrogen. So looking at my balanced equation, these two things decreased after we added the hydrogen, and the ammonia increased. Therefore, adding hydrogen caused our reaction to shift in the forward direction. How do we explain that? How do we explain why that happened? Well, we're going to do that by referring to kinetics and then also to the reaction quotient. Before we get there, just take a quick closer look at the changes in concentration. The hydrogen started off at this point here, at the beginning of the shift in equilibrium, and reached a new equilibrium concentration here. So the change in concentration for hydrogen as a result of the shift is this here. If you look at nitrogen's change in concentration, you'll notice it's much smaller. Why do you think that is? In fact, it's about 1/3, in fact, it's exactly 1/3 the amount of change for hydrogen. The explanation comes from the balanced equation. You get 1 mole of nitrogen disappearing for every 3 moles of hydrogen. So the change in nitrogen was much less dramatic than the change in hydrogen. Ammonia's change, it increased because it was being produced, not used up, and its change looks, to the naked eye, it looks kind of close to hydrogen's change, but in fact the ammonia's change would be 2/3, 2 to 3 ratio. It would be 2/3 the change of hydrogen. The ammonia's change should also be twice the nitrogen's change. Think of an ice table and the change line of the ice table, and that should make sense. Now let's explain what happened here with kinetics first and then equilibrium, the reaction quotient. With kinetics, we can note first of all that hydrogen in the original reaction was a reactant in the forward reaction. Okay, up here, hydrogen is a reactant in the forward reaction of that equation. Notice too that because we were initially at equilibrium, the forward and reverse rates were initially equal. That's the definition of equilibrium. Increasing concentration of hydrogen would cause, according to kinetics, the rate of the forward reaction to increase. However, the reverse reaction rate would be unaffected by that. So since hydrogen is a reactant in the forward reaction, adding more hydrogen will cause the forward reaction rate to increase. So now the forward rate is faster than the reverse rate, and that results in the equilibrium shifting forwards, or to the right. As we shift to the right, the ammonia will be produced while both the nitrogen and hydrogen will be consumed. However, the final hydrogen concentration still ends up being higher than it was before we added hydrogen. In other words, while the system can shift to reduce the stress, it's not able to eliminate the stress of added hydrogen altogether. There will, in the end, be a little bit extra hydrogen because we've added some to the system. The explanation from kinetics is a little more wordy than the explanation that can be done using the reaction quotient. This is a bit more of a mathematical explanation. We would start by noticing that at equilibrium, Q and K, the reaction quotient and the equilibrium constant, would have been equal before we added hydrogen. We look at the expression for Q and we see that hydrogen's concentration is in the denominator. So if we were to add some hydrogen to the system, increase its concentration, it will cause QC, the reaction quotient, to get smaller. Since Q is smaller, it's now less than Kc, and we've seen earlier in the equilibrium unit that when Q is smaller than K, the reaction will shift in the forward direction. And once we see a forward shift, the same final statement will get more ammonia and less nitrogen and hydrogen as a result. The final hydrogen, though, again, is still higher than it was before the addition of hydrogen at equilibrium. Here is another graph that shows a different stress. Pause the video and see if you can explain what's happened here to the original equilibrium and explain why that happened using either kinetics or the reaction quotient. So just like before, we had the same reaction at equilibrium here, nitrogen, ammonia, hydrogen, all at constant concentrations. But then we notice that the ammonia concentration showed a sudden spike. So somebody has added ammonia to the system. That was the stress. The system reacted by shifting backwards, so the ammonia concentration has dropped, and the nitrogen and the hydrogen concentrations have increased. The time 3 here is where equilibrium was reestablished because all 3 concentrations are now constant. To explain why that happened, If you added ammonia to the system, ammonia is a reactant in the reverse reaction. That caused the reverse reaction rate to increase, and now the reverse rate is faster than the forward rate, so the reaction shifted backwards. From an equilibrium constant in QC explanation, we could say adding ammonia caused QC to get larger, since ammonia is in the numerator of that expression. Since QC is now larger than KC, the reaction shifted backwards. A second stress is changing temperature. Now, this one's going to involve some memorizing. We know that changing temperature is the only stress that would change the value of Kc. If we think of the example we just had, imagine that we knew the concentrations initially, we knew these concentrations, and we know the concentrations at the end, where there's a new equilibrium. If we took those concentrations before and after and put them into the Kc expression, how would the result compare? Was Kc before the shift here the same as, larger than, less than the Kc after the shift? Well, the answer in this example would be that they were the same. Changing concentrations does nothing to affect Kc. The concentrations here are different than they were before the stress, but Kc did not change. However, when you change temperature, Kc does change. This is the only stress that changes the value of Kc. And here's your memorizing. If an endothermic reaction is being considered, Kc is larger at higher temperatures. Kc will increase when temperature is raised and decrease when temperature is lowered for endothermic reactions. Exothermic reactions have the opposite relationship with temperature. Kc there is larger at low temperatures, and Kc therefore increases when temperatures are cooled and decreases when temperatures are warmed up. From a kinetics perspective, we can note that temperature changes will affect the rates of both endothermic and exothermic processes. So if you have a reaction, A becomes B, and we think of it as exothermic, what we're saying there is that the forward reaction is exothermic, but notice the reverse reaction would be endothermic. So in any equilibrium, one direction is exothermic while the opposite direction is exothermic. They're the opposites. Temperature will affect the rates of both of those processes, so the forward and reverse reactions are affected by temperature. However, and this is the important piece, endothermic reaction rates are affected to a greater extent by temperature change than exothermic processes. The explanation for that is a little complicated, and it comes from the Arrhenius equation, which you might remember related to temperature and rate constants. If you think of a potential energy diagram for an exothermic process, notice that the forward reaction here has this activation energy, and the forward reaction there is exothermic, but the reverse reaction has this activation energy, and the reverse reaction is endothermic. The fact is that the endothermic direction will always have a larger activation energy than the exothermic process. Because of that, the endothermic process, the endothermic direction of the equilibrium, will always be affected to a greater extent by temperature change. So for example, raising temperature would cause both rates to increase, forward and reverse, but in this case here, the reverse rate would increase more because that's the endothermic process. Cooling the system would slow down both rates, but the reverse direction, the endothermic process, would be slowed down more than the forward reaction. So the endothermic process is affected to a greater degree by temperature change than the exothermic process. Here's our example with the same reaction, nitrogen, hydrogen making ammonia. Delta H is negative again, still exothermic. What's the effect of raising temperature on the production of ammonia here? Well, the kinetics explanation is that The forward reaction is exothermic, while the reverse reaction is endothermic. So forward reaction exothermic, reverse reaction endothermic. Increasing temperature increases both the forward and reverse rates. But the reverse rate, which is endothermic here, increases more than the forward rate. So now the reverse rate is larger than the forward rate, and the reaction shifts backwards. It shifts to the left. Therefore, there'll be less ammonia in the system. Since the ammonia is here on the right, shifting backwards will result in less ammonia in the system. From a reaction quotient perspective, we would argue that increasing temperature causes the equilibrium constant for this reaction to decrease. Now, why did I say that? The reaction as it was written was exothermic. Exothermic reactions, you remember, have larger equilibrium constants at low temperatures, and so if we're raising the temperature, the Kc will decrease for this reaction. Qc then is now going to be greater than Kc, and the reaction shifts backwards. So there's the explanation from the reaction quotient perspective. A third stress, changing the volume of the container, changing the pressure inside. This affects situations where gases are involved. We remember that pressure and volume are inversely related, Boyle's law from our gases unit. Increasing volume of a container reduces the pressure of gases inside. We also know just from a simple understanding of concentration that if you increase the volume of a container, you're reducing the concentrations of any gases inside. There's our equilibrium again, the Haber process. The question now is what would happen to the amount of ammonia in the system if we transferred it to a larger flask? So we have the system at equilibrium and we put it into a larger flask. Well, we're going to explain this from the QC perspective. All the concentrations and pressures will decrease because of the move to the larger flask. With larger volume, concentrations and pressures are going to be smaller. The denominator in the QC expression is going to decrease more than the numerator, right? The fraction here has concentrations of products and reactants, and we've just said that they're all going to decrease. However, when you look at the numerator, you'll notice that the concentration there is simply being squared, while in the denominator, our overall order is 4. We have something cubed and something to the power of 1. So in the numerator, our overall order is 2, just being squared, while in the denominator, the overall order is to the 4th power. Now, if you did the same thing to every concentration, doubled them or halved them, would the effect be the same on the top and on the bottom? No, it'll be greater on the bottom because of this higher order of exponents. So basically, mathematically, we're going to argue that the denominator in the QC expression in this example is going to decrease more than the numerator. If your denominator then is decreased more than the numerator, the fraction will get larger. QC gets larger. Therefore, QC is now bigger than KC, and the reaction will shift backwards, resulting in less ammonia. The older explanation for this, the explanation that I would not recommend for an AP free response question, argued something like this, and you might like to think this when you're doing a multiple choice question. If you were to increase the volume of the container, then all of the pressure inside will decrease. The total pressure will decrease. The system is going to try to raise the pressure as a result. And to raise the pressure, it's going to shift in a direction that produces more gas. Since there's 4 moles of gas here on the left and only 2 moles on the right, this reaction to produce more gas will shift backwards. All right, so there's perhaps a simpler explanation that might be useful when doing a multiple choice question. You raised the volume of the flask, that lowered the total pressure. the system's going to try to raise the pressure by producing more gas, and in this case, shifting backwards. Notice if there were equal amounts of gas on both sides, then there would be no shift. The system would not be able to relieve the stress. In QC, the order on the top and bottom would have been the same, and so QC would not change as a result. Putting everything together, here is a three stresses have been applied to our system. Can you explain what happened at the 3 steps? Pause the video and try to do that. So the system was originally at equilibrium, and then at T1 we noticed that the nitrogen concentration suddenly increased. So nitrogen was added to the system. Therefore, the system tried to remove the extra nitrogen by shifting forwards. There's one way to think about it. From a kinetics perspective, you would argue that more nitrogen caused the forward reaction rate to increase, therefore, and the reverse rate was unaffected. Therefore, the reaction shifted forwards. The nitrogen concentration dropped, the hydrogen concentration dropped by 3 times as much, theoretically, and the ammonia concentration increased because of that forward shift. From a reaction quotient perspective, we would argue that increasing the concentration of nitrogen caused QC to get smaller, and when QC is smaller, there's a forward shift in equilibrium. So there's 3 different ways to explain it, but on a free response question, only the kinetics or reaction quotient explanation would be helpful. At T2, we notice something a bit more complicated. You might be thinking initially that perhaps all 3 substances were suddenly added to the system, and I agree that's theoretically possible, but an easier explanation for why all 3 concentrations would increase, and it looks like they increased by the same amount, concentrations there increased because the volume of the container decreased. So the volume of the container decreased, that caused the concentrations of everything inside to go up. However, the denominator is going to be affected more than the numerator because it's got a higher overall order than the numerator, so the denominator increased more than the numerator. Therefore, Q got smaller. When Q gets smaller, the reaction shifts forwards. Another way to look at that is that when you increased the concentration by lowering the volume, all the pressures went up as well. The system's going to try to reduce the pressure by reducing the amount of gas. To reduce the amount of gas, it's going to take the nitrogen and the 3 hydrogens and convert that into 2 ammonias. So 4 moles of gas become 2 moles of gas. At time 3, after the new equilibrium had been established, we can see now that there's no sudden increase or decrease, but there is a shift that occurs. We can see that the nitrogen is increasing with hydrogen and the ammonia is decreasing. So this means there was a reverse shift happening here. So forward shift, and now a reverse shift. What would be causing the reverse shift? Well, we remember that this reaction was exothermic. Heat was on the right-hand side. A reverse shift would be caused by raising the temperature in this case. If you raised the temperature in this reaction, the system would try to remove some of the extra heat that we've added, and to remove heat, it would shift backwards away from heat in that reaction. There's a good multiple choice way of thinking about it. The harder way to explain it is from the reaction quotient or from the kinetics perspective. From the reaction quotient in Kc, we'd remember that when you raise temperature of an exothermic process, Kc gets smaller. Therefore, Q was larger than K, and that would explain why there was a reverse shift in equilibrium. So there is a little bit of a reversal in explaining after seeing a graph. A few other common questions and things to note. You may see a question that says, well, what happens if you add or remove a solid or a liquid? The answer is no effect. There's no shift, and you can explain it either by saying, because solids and liquids aren't in the expression for QC, QC is unchanged and therefore no shift. Or, since their concentrations are constant, removing solids and liquids does not affect the rates of forward and reverse reactions, so no shift will occur. Another common question asked about the addition of a catalyst. If you add a catalyst to a system at equilibrium, will there be a shift? The answer is no. A catalyst will lower the activation energy, which speeds up both the forward and reverse reactions. Since they speed up equally, there's no shift in equilibrium. If the system hadn't already been at equilibrium when you added the catalyst, it would simply reach equilibrium faster. But in the end, you'd have the same amount of product with the catalyst as you would have without the catalyst. You would have just made that faster. So catalysts do not affect equilibrium because both the forward and reverse rates speed up equally. A last example that you do see quite often is asking what happens if we add a noble gas, something like helium, neon, or argon. And this may seem a little strange because noble gases, we know, don't react with things, so there's not going to be any kind of chemical reaction. The answer is no effect. If you add a noble gas to the container, the total pressure inside the vessel does go up. So some people want to start thinking about, well, isn't that the same as when you lower the volume of the container, which also causes the pressure to go up? And the answer is no. Dalton's law explains why the total pressure here goes up. It's because you've added another gas. However, you didn't change any of the pressures that were already there. If you imagine you had a pressure of hydrogen, of nitrogen, and also of ammonia, and then we throw in helium gas, none of the pressures for hydrogen, ammonia, or nitrogen will change, but the total pressure does go up because there's another gas. So although the total pressure changes, none of the partial pressures change, therefore Q is unaffected. Another way to look at it is that there's no change in the equilibrium constant here, and from a kinetics perspective, the noble gas does not affect the rates of the forward or reverse reactions. Therefore, there's no change in there's no shift that will occur. This is probably the best explanation that QP and QC are unaffected. All right, let's just see if you fully understand. Here is a reaction at equilibrium, N2O4 decomposing to make two NO2s, and delta H is positive 58 kilojoules per mole of reaction. Here are several changes, several stresses. Can you predict the direction that the reaction will shift, if at all, in response to each change? Pause the video and see if you can do that. If you add some N2O4, the system is going to try to use up the N2O4 and shift in the forward direction. Another way to say that is that adding N2O4 will increase the rate of the forward reaction while leaving the reverse rate constant. Since the forward rate is now larger than the reverse rate, the reaction shifts forwards. Finally, you could look at the reaction quotient, NO2 squared over N2O4. Increasing N2O4 causes Q to get smaller, and that results in a forward shift because Q is now less than K. If you add NO2, the system will shift to the left. The system will try to get rid of the extra NO2, and in doing so, it will shift backwards. Alternatively, you could say, kinetics-wise, adding NO2 will speed up the reverse reaction rate while not affecting the forward rate. So now the reverse rate is larger than the forward. You get a backward shift. Increasing NO2 causes Q to be larger than K, which also results in a backward shift. So several ways to explain it. I'm going to stop doing the explanations and just reveal the answers. I'll reveal the answers using the simpler multiple choice thinking. If you remove some N2O4, the system's going to try to make some more N2O4. To make some more N2O4, it will shift backwards to the left. If you remove NO2, the system will try to make more NO2. To make more NO2, it'll shift forwards to the right. Adding helium has no effect on the equilibrium. Helium will cause the total pressure to go up, but doesn't affect any of the pressures that were there, neither pressure will change, and therefore Q is unaffected. There's no effect. Decreasing the volume of the container will cause the pressure to go up. The system will try to reduce that pressure by removing some gas. Since we have 2 moles and 1 mole, to reduce the amount of gas, the system will shift to the left. Increasing the volume is the opposite reasoning. The system's going to try to make more gas to raise the pressure, and so there'll be a forward shift to the right. Increasing temperature, this reaction was endothermic, so heat can be thought of as being on the left side. If you increase the temperature, you're going to add heat. The system's going to shift forwards to get rid of that extra heat. Alternatively, a more rigorous explanation would say increasing the temperature speeds up both the forward and reverse rates. However, the forward rate here, which is the endothermic process, is going to speed up more than the reverse rate. So there'll be a shift in the forward direction to the right. If you decrease the temperature, decreasing temperature will slow down both the forward and reverse rates. However, it will slow down the forward rate more than the reverse rate because the forward rate is endothermic. Since the forward rate slows down more than the reverse rate is going to be larger than the forward rate, and you'll see a reverse shift to the left. So there are Le Chatelier principle questions, both explanations and examples. You can now jump in and try some Webassign if you'd like, or some of the practice multiple choice questions that are online as well.